ladies and gentlemen, welcome to another webinar from Philips Lighting University. Today's webinar is titled Cities That Sense and Respond, and it will be presented to you by Professor Carlo Ratti, who is a director at MIT Senseable City Lab.
So my name is Carlo Ratti. I'm a professor of the practice of urban technologies at MIT, where I run a place called Senseable City Lab, and also a partner of the design office, Carlo Ratti Associati. So I'll just wanted to, I hope all of you are seeing my slides. I just want to share with you something about what we call sensible cities. And this was just mentioned of cities that are able to sense and respond to citizens. But to look at this, I wanted to start with this picture. And if you look at this picture, it's something that people really used to be fascinated in the 1990s. In the 1990s, people thought that because of digital, our life would become increasingly virtual. So virtual, there's some people such as Gilder, an American writer, in 1995 mentioned and thought that cities one day would disappear. Gilder wrote, "We are headed for the death of cities. Cities are leftover baggage from the industrial era." Well, what does this tell you? The first thing it tells you is, never make predictions about the future. Because no prediction could have been more wrong than the one by Gilder. We now know the cities have been thriving over the past few decades. That's a picture from Tianjin in China. China this century might actually build more cities than what humanity has ever built. And we also know that since 2008, half of the world's population lives in cities. And by 2030, this number might swell to almost 5 billion. So what has happened is that digital hasn't killed physical space, but somehow digital and physical are recombining. They're creating a new hybrid dimension in between bits and atoms, digital and physical. Another way to think about it is about the internet becoming Internet of Things, entering our objects, our homes, our cities, and providing us the ability to interact with the built environment in new ways. And that's really what we're trying to explore at the Senseable City Lab. And when you look at this, kind of the glue behind a lot of what we are talking about is sensing and actuating loops. There's a lot of feedback loops. We can sense something in the city, in the building, and we can respond to that. And I think a lot of this happens with lighting, for instance. We can know in real time what is going on, we can sense it, and then we can respond to this information. But let me give you a few examples. If you look at this is the city of Lisbon. It's a city of Lisbon is captured using billions and billions of data points from the taxi network. And we couldn't understand the city like this just a few years ago. But now we can because of all the sensors we have. Incidentally, this visualization that was done by Pedro Cruz from our lab at MIT was exhibited at the MoMA, the Museum of Modern Art in New York. It gives you a sense of how we can understand the city in a different way today and how this information could be valuable. Now, that's exactly the same information in New York City. Here you see the taxis through every pickup and drop-off. And what you see here is a special point, is JFK Airport. Every yellow dot is a pickup, every blue dot is a drop-off. If you zoom out, we were down there on the image at the airport, but then you can see Manhattan and all of the boroughs. Now, if you have this map, you know everything about the taxi mobility in New York, and then you can ask yourself, what if we were ready to share mobility more? And you know what? If you take 82 points in Manhattan, in the course of the year, you got hundreds of thousands of trips connecting those 2 points. This is any 2 points. So the question then is, these days we like to share many things. How many of these trips could be shared between people? And we started looking at this question from a mathematical point of view. Unfortunately, when you got such large amount of data, what people usually call big data, then you need to develop big mathematics, new mathematics to address it. So you couldn't solve this problem with traditional mathematics. What we did, we developed a system called shareability networks, which is based on network science in order to respond to this. And here you see some of these networks that densify, telling you how many trips could be shared. And here you see some of the results, which are quite interesting, that in New York, you could take everybody to destination exactly when they need to be there, give or take 1, 2, or 3 minutes, but with 40% less vehicles than ones we have today. So we could cut fleets by 40% and still satisfy the mobility demand of New York. Or most other cities, actually. We got a paper coming out next month that shows that this is applicable to most cities across the planet. And this is interesting. When we did this, actually, the paper is quite recent, but the first results came out 4 years ago, and they came to attention of Uber. And since then, we started a collaboration with Uber about sharing. And as you might know, Uber Pool does exactly this. Uber Pool allows 2 trips to be shared. It's interesting then, when the first results came out, the New York Times did a review and said this is interesting mathematics, interesting research, but guess what? New Yorkers will never want to share their car, their vehicle with anybody else. Well, it turns out, as Uber Pool and many other services show, that actually sharing of the vehicle has become very, very popular. I believe that in San Francisco now, Uber Pool is over 50% of all trips taken by Uber. And when you share a vehicle, it means it's one less vehicle on the road, which means less traffic, less energy consumption, and less pollution in the city. Now, this is what is happening already today, thanks to data. If you look at the future, you can look at how the car, as you see in this picture, is becoming like a computer on wheels. This shows you all the sensors that you already have in the car today, and some of the sensors that you might have tomorrow. What you see here is actually 2 little things on the top of this car, like the human eye. They basically do a 3-dimensional scan of the environment, like what you see here, which is like a 3D model. And then you feed this 3D model plus camera data into computers. You use artificial intelligence and bam, the car starts to drive itself. And this is very interesting, first of all, because it's reality, it's not the future. As we speak, there are many fleets of self-driving cars, some of them accessible to the public. As you might know, Uber is running an experiment in San Francisco and Pittsburgh, while Singapore has the first fleet of publicly accessible self-driving cars. And when this happens, everything changes again with mobility, because then the car can give you a lift in the morning when you go to your office, and then can give a lift to somebody else in your family or to anybody else in the city. So what you're doing, you're blurring the distinction between public and private transportation. If you combine what I was saying before about the sharing of the ride in New York and other cities with this, which is the sharing of the vehicle itself, so the sharing of the car, the combination of both can actually give you a system, a city, where you could take everybody to destination when they need to be there, but with just a fraction of the vehicles we have today, which will mean much less cars and much less parking spaces around ourselves. A few years from now, when we look at when everything will be digitized and self-driving, other things might change, such as this one. As you know, this is a well-known traffic light, and traffic lights arrived on our streets when actually cars arrived on our streets. But if you think about an intelligent system where every car knows where every other car is, then you don't need traffic lights anymore. You can keep on going with us just without bumping into somebody else.
Specifically designed for autonomous
like
vehicles.
This.
By utilizing much more of the intersection at any given time than traffic signals and stop signs, the AIM reservation protocol has the potential to dramatically reduce congestion and therefore fuel usage.
And this is just a little snapshot from a project that's been looking at this. We've been doing a lot of work on intersections at our lab at MIT, the Senseable City Lab. And what you see here, for instance, it's a typical intersection. You see, it seems very simple, but you've got many different trajectories that can mix up. And here you can see how you can actually look at them, all other parameters being the same. And what you see here is, oops, apologies, I wanted to just reduce with the sound. And what you see here is the difference between a traditional way of managing an intersection, in this case a real intersection in Singapore, and to the left, managed with the most sophisticated traffic light system you have today, and to the right, with a slot-based system. All other parameters, including safety, being equal. And look at the difference in terms of managing that place to the left and to the right in terms of delays and cars waiting. And the intersection is usually the bottleneck of the full mobility system, the mobility network. So fixing the intersection, you actually have a big impact that reverberates across the whole network. I wanted to share also another project about self-driving, just because this project is also very close to Philips headquarters, and it's a project in Amsterdam. What you see here is a map of Amsterdam. It's a beautiful city. It's a city where, at least in the city center, you don't have many roads, but you have a lot of canals. And so by starting working with the mayor's office and AMS and the CTO of the city, so I think, what if you could develop a system of self-driving boats, call them rowboats? They could do what boats do today, like move around freight. It's a DHL boat in Amsterdam, or that's a taxi, water taxi in Amsterdam. But you can do it in a different way. You can do it in a much more efficient way, and also you can use them in order to create a temporary infrastructure. What you see here is like a temporary bridge. You can assemble. It becomes like a self-assembling system when you need a platform for an event or a bridge for an emergency or anything else. You can have all these little pixels moving around. That's a project we just started a few months ago, but it doesn't do anything new. If you want, it does what we've done for hundreds of years. You see here Venice, where people with gondolas come together and create a temporary bridge, but in kind of a different way. I think that's the key thing about technology, when it helps us to do the old things in a new way. I'll show you just the first mock-ups here. The project started a few months ago. You see here the way we're trying to design the vehicle in a way that it's more very easy to control, a bit like a quadcopter. But it really allows you to have a lot of flexibility. In this, you see in the little video now with this kind of 4 controllable motors, how you can be very, very flexible. Then you add the artificial intelligence in this little thing that's a scale model. To be bigger in reality, will actually be able to drive itself. So you see some footage from just a couple of months ago in Amsterdam in December. You see how controllable this is? And then here you see some footage also from the camera on the boat itself. And you make it so controllable that this can also become like move in a lateral way in this sense. All right. I wanted to finish by sharing with you some other projects, and in this case in particular, what we have is something related to offices, and how offices used to work and cities used to work, and how they work today. And what you see, for instance, is something that Le Corbusier, one of the most renowned architects of the past century, was writing about in the early 20th century, which is about how we should divide in a city everything: the place for sleeping, the place for working, the place for leisure, and the connections between them. But you see it there on the picture to the left. But if you think about the city, well, that the city is not very efficient. It's a city where you have a lot of unused spaces for working, which are empty most of the time, or spaces for cities. So it's no surprise that since the 1960s, many people started thinking about how we can do mixed-use developments with really different functions over space. And we believe that today, digital is changing that once again. It's creating a new transition between public and private space, and a new way to think about the very structure of the buildings we live in. Let me give you an example taken by our campus at MIT. So what you see here is Boston. See MIT like a small city inside the city. See Harvard there, don't bother, up there. And then MIT was one of the first campuses worldwide to be totally layered and covered with technology, including Wi-Fi at the beginning. And that has produced a big change in the way of working. Here you see to the left the way of working once upon a time, and to the right the way of working today. Well, it's a bit biased. To the left you see the most appalling computer room you could think about. And then to the right, you see a beautiful sunny day. It was not like this just a couple of days ago. But, it gives you a sense, the same thing that's been happening in office design all over the world, going from something like this, that's Jacques Tati's playtime, making fun of traditional cubicles, but still being used all over the world, to something like this, a new way of working. And well, so we ask ourselves, how is this changing? Well, technology is changing the way we work, but technology can also be the way to measure some of these changes. So what we've been doing is starting measuring the signal from all of the hotspots on campus, and then you can see where people are at different time of the day. For instance, here at the top, you see the overall activity curve in Boston, on the MIT campus. You see people getting to campus. The first to the left is Monday. At the top, you see around 9 o'clock. Some people leaving at 5 o'clock. Most people keep on working till late at night. And then in the middle of the night, still a lot of activity on the network. The same thing on Monday, on Tuesday, on Wednesday, on Thursday. Not on Friday, to the right, where activity slips away quite quickly on campus. And then Saturday and Sunday are almost like 2 normal days. You remove the 9 to 5 people, but you got 2 days with a lot of activity. Something quite interesting, every Sunday night you have a little dent. You see it there at the top to the right of the image. And there's a little dent between 9 and 10 p.m. and that's when people say, wow, tomorrow is Monday again. And then you go back to doing all the things you hadn't finished. So if you do this, you got like an occupancy curve for the overall campus, like I showed you, but you can have it for every space on the campus, for every room. And that's what you see. You can then analyze it. You can look at frequencies. You can look at clustering, like you see here. And what you find is really exactly what I was telling you, is the fact that basically spaces are being used in a much more flexible way over the course of time, and technology is liberating us from some of the strictures of the past, some of the constraints in the past. It can help us use space in a much more efficient and flexible way. And then what we can do today as well is looking at, how many then papers and patents come out of each building. So also the productivity of people. You can look at the diversity of the different buildings. You can look at the network of how people collaborate. Really trying to crack down this equation about how space is bringing us together to do things together. So, if you want, MIT is nothing else than a bunch of people which are co-located on the campus in different ways. They exchange information via email, telephone, and digital networks, and they produce something, in our case, primarily papers and patents. So when you combine all of that, you really can start to crack down on this equation about spaces for collaboration and research. And we're actually using today a lot of this information through our design office to design many of these spaces, real spaces. What you see here is one of the largest co-working spaces in Southern Europe. It's in Milan. It was just finished, and really thought about as an interaction space. You see, this is another space in South America where the courtyards becomes interaction spaces for people to come together and exchange ideas. And you see this in another project that we've been doing, which is interesting because, again, it tries to have people come together, but also uses technology in this case to promote some of those contexts. And the way it does it is by really having people be able to use an app about the building. And then this app can tell you occupancy in real time, so you can have your preferences in terms of lighting, heating, cooling. But also it helps people to check into the building, to book their rooms, and to do something like similar to think about a Foursquare, where you know where people are, and you can share the information with your friends. So again, it becomes a locational platform to help people come together and do things together and work together. So you see again, both heating, cooling, and lighting all respond to occupancy, and they become controllable through a very simple app for the building. And that's something part of the broader research we're doing. You see it here. It's about in this case the fact that we're wasting so much energy heating or cooling unoccupied buildings. And this is a paper that we did. We looked at the MIT campus again. You look at occupancy, you look at energy, and there's no correlation between the two at all. So we use a lot of energy to heat and cool empty spaces. And so we started thinking about, can we go another way? Can we think about local warming, about just using heating and cooling in a localized way, following people? You see here on this slide, we started at MIT, we tested it outside MIT. You had this kind of bubble of heat that would follow you as you enter the campus. That's the main entrance at 77 Massachusetts Avenue. When we did it, some people freaked out a little bit. Most people had a lot of fun. So then we did an installation in order to test the concept on a broader scale for an art and architecture installation exhibition called the Venice Biennale. I'll show you a little video about it now. All right, so and here you see the video showing this, and I want to finish with another thing. As buildings start to respond to us in terms of heating, cooling, lighting, they can also respond to us in terms of furniture, and that's a project we've been doing with Vitra, one of the major players in furniture production in the world, based in Switzerland. And what you see here is thinking about the space around ourselves that can become reconfigurable, like pixels. You can move them up and down by putting your hand. Now, moving them up and down, you can combine them to do different forms, such as this one, for relaxing your space, for doing some work with friends. And when you combine it together, you can also make it movable with a little actuator. So in the video now, you'll see how this can become like a flexible, movable, controllable environment in your home. Again, another consequence of this higher flexibility we have in using the spaces we inhabit. And I think with this project, my half hour has expired. So this was to give you just a little glimpse of how Internet of Things is changing our cities, is changing mobility, is changing mobility in general for cars or for other mobility systems. It is changing the places we live and work and making them more responsive. So all of all, as it was mentioned before in the introduction, about a city that is able to sense and respond.